some of their structures, and we started to look at some of this naming with these like different, where we talked about having the chain and then the different pieces coming off of that. We're going to continue that today, and then get into a little bit more about shapes and looking at these things in 3 dimensions. All right, so one thing that sometimes comes up in this type of work, this type of activity, this naming, is it's really easy to fall into the trap of always looking at the horizontal line or the horizontal zigzag as the main one, when it may actually not be the correct one to name from. So take a look at this structure right here. All right, so we might look at that structure and say, okay, the way we're going to start naming this, we're going to look across. We see 4 carbons, 1, 2, 3, 4, with something coming off the 2 and the 3. So it's a 2, 3 something butane. Why is that wrong here? Why is the parent of this not butane? It's what? It's pentane. Why? Yeah, because we always have to look for the longest continuous chain, which may not be horizontal. So in this case, the correct way to number and name this would be to go 1, 2, 3, 4, 5. Recognize that you have methyl substituents coming off of 2 and 3. And so we would name this 2, 3, dimethylpentane. Why did I name starting from the bottom instead of starting from the top? Or why did I number starting from the bottom instead of starting from the top?
Branches start down there and we don't want it to be 4 or 5.
Right, exactly. We want the branching things to be closest to 1. So if we started from the top going down, that would be 3, 4 dimethylpentane instead of 2, 3. So 2, 3 has lower numbers, so we go with that one instead. All right. So let's look at what, so far all these examples, we've used methyl, this 1 carbon group coming off. But of course, there's lots of different things that can be coming off. So let's take a look at some other examples of things that might be hanging off of our main chain. We'll make a little table of the name and then the shape and kind of how it connects. So we'll say methyl is going to be a single carbon group, and I'm going to make a little zigzag line to just say that's connecting to this, whatever, to the chain. So that's our 1 carbon that's coming off of the chain. It is also totally okay, and you'll see it a lot just to avoid confusion, sometimes to write CH3 there, to use the condensed formula instead, just so we know that it's not something we forgot, that we actually mean there's a carbon there, and then it should be CH3. If you have a 2 carbon group coming off of somewhere, we call that ethyl, just like ethane was the 2 carbon hydrogen parent. So if we have, here's our main chain, if we have 2 carbons coming off, that's ethyl. 1, 2. Notice those carbons are connected to each other. If we just have 2 separate carbons in the structure, that's going to be dimethyl, which we already talked about. They have to be connected to each other to be an ethyl group altogether. Can you guess what a 3 carbon group might be? Propyl, yeah. And in fact, there's 2 different types of propyl groups because of now we have some isomerization where we can connect to 2 different types. So we've got propyl, which is, as you'd expect, a 3 carbon group like this. And we also have isopropyl, which is a 3 carbon group that connects to the middle of that chain. So it's still a 3-carbon group, 1, 2, 3, but it's coming off of or it's connecting to the main chain by the middle rather than by one of the ends, and so we call that an isopropyl group. And then sometimes, the book doesn't do this, but sometimes for clarity, this regular one where it's connected to the end is called N-propyl instead of just propyl, just so there's not confusion. So you can have N-propyl and isopropyl. I believe the book calls N-propyl just propyl. Okay, and then you've got all the butyls. There's actually, the more carbons you add, the more different ways there are to connect things. So there's a few different ways we can connect butyl groups to a main chain. We'll start with the regular N-butyl, which would be a 4-carbon chain. Yep. So let me number that, make sure that's right. 1, 2, 3, 4. Now to have an N-butyl group on your structure, that means it's going to have to be a pretty big structure, because really that's a lot of carbons, and that's likely going to be making part of the main chain. So anything with an N-butyl group on it is going to be bigger or is going to have something with a higher priority, which we'll get into later. Okay, so just like with propyl, we can also connect to a different spot on the butyl group, but perhaps confusingly, instead of being called isobutyl, it's called sec-butyl or S-butyl. And so that's where we have our main chain, and it's still a regular 4-carbon butyl group, but it's connected 1 carbon in on a secondary carbon. So for the first quiz, one of the questions was to find out about what a primary alcohol is. You can have primary, secondary, tertiary. So this is coming off of a secondary carbon, which is a carbon in the middle of the chain. You can also have isobutyl, which is that group that we looked at last time. So it's actually it's actually an isomer of butane. A totally different structure. It's really, as we said last time, it's really 2-methyl propane, but it's commonly known as isobutyl. And then you can also connect to the very middle of that group, the tertiary carbon, and so that's called tert-butyl or T-butyl. And there's our 4 carbons coming off, but we're connected right to the middle. Tert-butyl is an important group because as you can see, it's very crowded. There's a lot of stuff around there, especially if you recognize that the ends of those lines are CH3 groups in themselves, so they have even more atoms kind of coming off of them. So when there's a tert-butyl group on a structure, you can kind of make it do some interesting things because that takes up so much space that it can kind of force molecules into particular positions. All right, so putting all this stuff together then, if you've gone through some of the homework, you've already practiced a little bit of this in Chapter 3. Let's take all these groups and put them on some chains and try to figure out what those structures might be called. So I'm going to draw a couple structures, and I want you, either on your own or in your groups, to discuss and try to name them using the skills that we learned last time, but with some of these new groups. Okay, there's one. Oops, hold on, that's all right. Don't worry if they're right or wrong, but just try to come to some names that you and your group think make sense at this point, and we'll talk about the right answers and why they might be different from yours. Talk to people around you, look back in your notes. All right, did you give these a try? Okay, let's go through it together and see what we come up with. So for the first one, what is the parent structure? What's the longest chain? It's the what? It's a line. Okay, let's count it out and see. So we got to count it out and check. 1, 2, 3, 4, 5, 6, 7. That's pretty long. Did anybody find a longer one? Yeah, it's a little longer if we go 1, 2, 3, 4, 5, 6, 7. Correct one. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So it's always helpful, I think, especially with these bigger structures, to actually draw the numbers on there so that you can really see where everything's coming off of. And then we can highlight those different groups that are coming off of it. So looks like we've got 2 things coming off that are not part of the main chain. What are those groups called? What? Methyl is the first one. What's the other one? Isopropyl, right. It's a 3-carbon group that's attached via the middle. So the way we're going to name this is, generally this is done in alphabetical order. So I for isopropyl comes before M for methyl. So we usually call this 5 isopropyl 2-methyl octane. Now things like that alphabetical order thing, I'm not going to be too worried about that for our quizzes and exams. If you have a unique name that describes that structure itself with the correct parent and everything, then you're okay. So any questions about how I came up with that name? Yeah, yes ma'am.
So, why wouldn't you put a comma?
Yeah, good question. Why is there no comma here? In these names, commas only separate numbers from other numbers, and the dashes separate numbers from words. All right, what about this next one? How are we going to name this one? Where's the longest chain here? Okay, so we're going to start. Hang on, let me see what you're saying. So you're saying start up here?
I'm not sure.
You're not sure? Start over here? Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Anybody find a longer one than that? Is there another 8 chain? There is one other one. So there's actually 2 possible ways to name this structure. We'll see if there's a difference in a minute. Yeah.
Like the top, like loop it.
Yeah, you can kind of loop around from the top, right? So you go 1, 2, 3, 4, 5, 6, 7, 8. It seems untidy. I mean, that's chemistry. Sometimes, if that's the thing you make, that's the thing you make. So let's take a look at the different possible ways of naming it and see if that actually presents a problem or not. All right. So if we do it, let's do it that first way, since it was the first way that we... So if we did it that way, this would be an octane. And the 2 groups are this one and this one. Which, by the way, you can have more than 2 groups. These structures both just happen to have 2 different things coming off. All right, so one of those, they're both coming off of carbon number 4. One is an isopropyl group like before, and what's the other one? A propyl, yeah, a propyl or N-propyl, regular propyl group. So we would call this one 4 isopropyl, 4 propyl, octane. So what would be the name if we did that loopy thing instead? If we started from the upper right and kind of went around to the right? It'd be the same name, yeah. So in this case, it wouldn't make any difference. If it does make a difference, if we did have a structure that made a difference, which I'll try not to do anything like that, but where it was really that close, you can use things like the numbers for the tiebreakers. So we want the lowest numbers, just like with the either side of the chain. So if you can make one that's a 2-3 and the other one's a 4-5, then you go with the 2-3. We'll try not to see any that are that complicated here. All right. Questions about this? Let's try one more, and let's see if everybody can get this one now that we've practiced a little bit. It's a big one. This is also, this is also an example from the book. All right, everybody give that one a try. Actually, you know what? Hold on. I'm going to add one more thing. All right, you got this one? Maybe? All right, let's take a look at it. So how many carbons did you find in the chain here? 10, yes. So this is a decane. Did you start numbering from the left or the right? From the right, yeah, because that's going to give you the lower numbers. If we number from left or from right to left, as I've got it written here, our substituents are at 2, 3, 5, 6, and 8. If we went from left to right, we would be at 3, 5, 6, 8, and 9, which are higher numbers. So we want to go with the lower numbers. All right, so let's name this whole thing out. So on carbon 5, we've got an isopropyl group, so that's going to go first, just because of alphabetical order. So 5 isopropyl. And then we have 4 methyl groups at 2, 3, 6, and 8. So we put all those together like this: 2, 3, 6, 8. And the word for 4 is tetra. So tetramethyl decane. Yes, Paul. No, anytime there's more than one. So yeah. Yeah, so if there were, I don't know if everybody heard that, but Nicole's question was, do you only use those prefixes with methyl? And the answer is no. Anytime there's more than one of a particular substituent. So if there had been isopropyl groups at 2, 3, 6, and 8, we could have called this tetraisopropyl in the same way. So you're going to use that prefix whenever. So there's no prefix if there's only one of them. Then if there's 2, it's di, tri, tetra, penta, just like when you're naming the inorganic compounds for dead. Yeah.
What if, like, on the number 2, there was 2 methyls coming off? Would that be separate then? It would be like 2 dimethyls, and then the 3, 6, and 8 would just be.
Good question. No, they would all still go together. So you'd call that 2, 2, 3, 6 tetramethyl. So you have a separate number for each methyl group, and if they're on the same carbon, you just use that same number again. So if like the ones that we did before the other day, we'd have like 2, 2 dimethyl if they're on the same carbon. Other questions? Okay, so please practice these. Please keep in mind, especially now as we get into newer stuff, the quizzes are not that's not like your homework. That's just supposed to be a quick check on this stuff. Please make sure you're going through all the homework in the book so that you practice this. If you do a whole bunch of these, as there are in the book, and you can see the solutions on Blackboard, there's nothing else new really that you can run into. Alkanes are alkanes. So once you've got a lot of practice with them, you've seen all these different groups and different ways they're arranged, then you should be good. But it is going to take practice to just do this over and over again with a bunch of different ones. All right, let's add something else in the mix here. So next we're going to talk about cycloalkanes. Which are alkanes that connect around to each other in a ring. So if this is pentane, then we could connect that around to itself, and this becomes cyclopentane. So it's simply named for the number of carbons in the ring with cyclo in front. One thing to watch out for, especially when we're dealing with these line angle structures where we don't see all the atoms, is the formulas are going to be different. So pentane is C5H12. If you imagine building that, you can try it later if you want. If you built a model of pentane, you'd have the 3 hydrogen, the CH3s on each side. If you then went to connect those into a ring, what would you have to do to give it room to connect, for the ends to connect?
Some hydrogen to it.
Yeah, you'd have to take off one of the hydrogens from each side so that there's a spot for that stick to go to connect it up. If you don't believe me, build it and try it. But this one ends up being C5H10. So whereas pentane is CH3, CH2, 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 CH3, cyclopentane, there isn't really a great way of writing it in one line, but we can write it like this. Okay, so it's CH2s all the way around because carbon can only have 4 bonds, so there can't be any CH3s inside the ring. So that leads us to a couple of terms. Saturated and unsaturated. A saturated hydrocarbon is one that has as many hydrogens as possible, which usually is going to be our standard alkanes that have a formula of CnH2n plus 2. So all the ones we've just been dealing with are what we call saturated hydrocarbons, saturated alkanes, because there's no way we can squeeze any more hydrogen in there. So if you have less than or fewer than 2n plus 2 hydrogens, you'd have what's called an unsaturated structure. Which is just going to be the same number of carbons with fewer hydrogens. So pentane is saturated, cyclopentane is unsaturated because there are fewer hydrogens. What is another way to get an unsaturated structure besides a ring, do you think? What's another way that you can have fewer hydrogens in a structure? Yeah, double or triple bonds is the other way to get unsaturated structures. So we'll get to that in the next chapter, but double or triple bonds will also decrease the number of hydrogens. That's where we get the terms like saturated fats and unsaturated fats. Those fatty acid chains, saturated fats are all straight chain alkanes, long straight chain alkanes like 12 to 18 carbons. Unsaturated fats have double bonds in them, and so you have less hydrogen. And they can be monounsaturated, meaning one double bond, or polyunsaturated, meaning multiple double bonds. If you've heard of things like omega-3, that means 3 carbons from the end, you have a double bond, because omega is the end, so 3 carbons from the end is a double bond. So that's where some of those terms come from, and we'll deal more with that in the next chapter. So when we name with these things, nothing else changes, except that the cycloalkane is usually the parent just because it's bigger. Not always, but usually it is. So if you have a structure like this, actually let's do that, and you're trying to name it, you can't go like this. 1, 2, 3, 4, 5, 6, 7. That's not the parent because that's not one thing. That's like in a part of it's in the ring and part of it's on the thing that's coming off the ring. So we can't do that. So we call the substituent, or we call the parent whatever's bigger, either the chain or the ring. In this case, the chain is 4 carbons, the ring is 6 carbons, so the ring is going to be the parent. Just for fun, let's throw something else on there. So let's say we have this. So now when we number our carbons, we have more choices with a ring because you can start anywhere. You don't have to start on one of the ends. So we have to make sure to pick our starting spot nicely so that we get the best numbering, the lowest numbering. And the best way to do that here is to call this one and then go around clockwise. You don't have to go around clockwise. It can be clockwise or counterclockwise, whatever gives you the lower numbers and whatever gives you the best, the lowest number on the lowest alphabetical order. So this one would be 1-butyl 2-methyl cyclohexane. Does anybody want to take a guess? What's the smallest cycloalkane that you can have? How many carbons would be in the smallest one, or what would its name be? Close. What? You can do 3, right? You can make a triangle. That's the smallest shape. That's the fewest corners of a shape that you can have. You can have a triangle, which would be cyclopropane. As you might imagine, that is pretty reactive because if you try to make a cyclopropane with these models, you'll actually snap the bonds because you have to bend them. What's the ideal bond for a carbon, for an sp3 carbon? What's the ideal angle for a tetrahedral carbon?
109.
About 110, yeah, 109.5, 110, right? What's the angle inside of a triangle? Going all the way back to 10th grade or whatever. 8th grade, I don't know when you did your geometry. What's the angle inside of a triangle? An equilateral triangle. No? Guesses? It's 60, yeah, 60. So there's a big difference between 110 degrees, which is like about that, and 60 degrees, which is like that. So those bonds are extremely strained in those structures, and we can take advantage of that for reactivity and make it do stuff. So as you get really small ones, they end up getting a little bit more strained and more reactive. But yeah, you can have cyclopropane, cyclobutane, and then all the way up to whatever. All right, let's play with some models. So next we're going to look at conformations of alkanes. Conformations are ways of changing the structure by rotating bonds. These are not different structures. These are not isomers. The way we talked about isomers last time, constitutional isomers, where you had to pull things apart and rearrange them. Conformations are not isomers. They're simply ways of rotating the bond and then looking at the way the structure changes as the bond rotates. So, yeah. So as we made the structures, you could sort of like flip them around to see all the different ways that they rotate. All right. So everybody take your model kit or kits or whatever. Take 2 of the carbon atoms. Doesn't matter what color. Just make sure they're the tetrahedral ones, not the other shaped ones. And let's make a molecule of ethane. So everybody make a molecule of ethane. And this time, make it, you don't have to put the little balls on the end for the hydrogen, but at least get all the sticks on there. Something like that. I use a different color on one carbon, but you don't have to do that. You got something like this. Now, play with it a little bit. Rotate that carbon-carbon bond. And notice there are basically 2 kind of clearly different positions that you can put that structure in. See that? What 2 do you think I'm talking about? And obviously it can go all the way around, but there's kind of like 2 extremes as it goes around. Any ideas what those would be? Guesses? I'll give you a hint. One of them is called staggered. guess what that would look like? Yeah, right. Right. So in the staggered conformation, if we look straight on like this, you can see that the hydrogens on one carbon kind of split the ones in the back, the other one, all the way around. So if you look at it really straight, it really kind of looks like a nice six-pointed star almost. We call it the staggered conformation. Okay. And then the opposite of that we call the eclipsed conformation, where you would line them all up like this. So take a look at your models and make sure that you can see both of those. And then we're going to talk about how we would draw this. So you can make it staggered, you can make it eclipsed. Now drawing those in the way that we've been drawing them, you can do it, you can use dashes and wedges. It can be a little bit hard to see. So I'm going to do it here, but then I'm going to show you a better way to express this. So if I want to show the staggered conformation of ethane, I could draw a carbon-carbon bond like this. Kind of look at it on the side. And then what I'm seeing here is there's a hydrogen that's in the plane on each side, and they're opposite each other. And then there's one on a dash and one on a wedge on each side, and they're kind of opposite each other too. So like that and like that. So set your model in a staggered conformation and make sure that you can line up what you see physically in your model with what you just drew on paper or what I drew on the screen. You can see that difference. And then let's turn it to the eclipsed conformation. Let's just turn the rightmost carbon, the one on the right. So that means that our left carbon is going to stay the same. And the right one is going to change like this. Once again, look at your model, look at the drawing, make sure that it makes sense, that you can see how we drew what we see in the model. All right. So that works, and you can see that, but it's not as obvious as when I went like this and I showed you it head on. If you look at this thing head on, you can really see, oh yeah, that's eclipsed, that's all lined up, or that's staggered. So there's a different way that we can draw this structure called a Newman projection, where we basically draw what we see looking straight down a bond. Now that's great, but we need to actually express like what the front and the back is, otherwise we're going to be confused. So the way this works is we draw something that looks like this. It's a circle with a kind of like triangle thingy in the front, and then some things coming off the back. And the way we interpret this is the point at where those lines come together, right there in the middle, we call that the front carbon. And then the circle is the back carbon. So if I then add the atoms here, if these are our hydrogens, which conformation have I just drawn here? Staggered or eclipsed? Yeah, that's staggered, and we can see how it's staggered pretty clearly with that now, right? So again, as we did before, make your staggered conformation with your model. Look down from one to the other, and make sure that it lines up with what we just drew. So that means you're going to put one of them up. One of the ones in front is going to be up. And you should have something like that, and you should see all of those hydrogens expressed in that diagram. Now, there's nothing special about putting that front one up. We could have put the front one down and drawn it like this. That's fine too. But we decided to do it like this. Or I decided to do it like that. Do it however you want. But let's all just make sure that you can see that. You've got a front carbon, which is that point, and then the back carbon, which is the circle. Now we're going to draw the eclipsed conformation. With the eclipsed conformation, we'll keep the front one, or we'll keep the back one steady, and we'll redraw the front one. We can't really draw them exactly on top of each other, or we won't be able to see anything, because obviously eclipse means they're totally lined up. So we're going to draw them just slightly offset, just so we can see it well. So our eclipse conformation, our back we're going to leave the same, like this. Those are the 3 hydrogens in the back. I'm going to move the front ones over a little bit. And we're not going to totally put them in front just because then we couldn't see them. We're going to draw it like this, and this is called eclipsed. Yes?
Do you have to draw the hydrogen on, or no? Like for it to be a Newman projection? Like if you were to ask us to draw a Newman projection and we just drew the lines, is that okay?
The lines are fine because generally we're going to be doing this with larger structures than just ethane. So you would write whatever's actually connected on there. Does that make sense? Like that could be, whatever's connected to those bonds is whatever is actually connected in that structure. It may be hydrogen, it might be something else.
So so if it is hydrogen, you have to write hydrogen. And then you can't just like leave like the other structure, we just
Right.
omit the hydrogen. We can't do that.
Yeah, we would generally draw it all out with these because we're looking at all the specific positions. So let's try that with a bigger structure. So now, if you've got some people around at your table, combine a couple of your ethanes together to make a butane. If you're on your own or you want your own, just make your own butane. I'm running out of sticks here, so mine's going to be a little bit lopsided. So let's just make a nice butane. And just because I have them here, I'm going to use some different colors, but feel free to use whatever you've got. So with butane, there isn't just a Newman projection of butane now, because we've got different bonds we could look at. Right? We could look at from 1 to 2, and we could say, okay, well, we can look at this rotation as this goes around. Or we could look from 2 to 3, and look at this rotation as that goes around. And then this one, we can actually look from like 2 to 1, and kind of look this way with that one in front. So there's various ways we can do this. So there isn't just a Newman projection. We have to be really specific about how we're looking at it. What type of projection are we looking at? So let's look specifically at butane down the 2 to 3 bond. So if we look at a butane like this, here's our butane structure. 1, 2, 3, 4. And we want to draw a Newman projection looking down from carbon 2 to 3. So that's going to be this direction. So 2 is our front carbon, and 3 is our back carbon. Now this one, the way we have it drawn here, it's kind of staggered already. So this is where the models can be really helpful, because you can build that. You can build what we had the line structure for. And then we can say, all right, we want to take this perspective looking from carbon 2 to carbon 3. So that means we're going to turn it around and look straight down this way like that. You see that? That's how we got 2 to 3. Just like it is up there. So there's our structure, 2 to 3, 2 to 3. So let's draw that. That means that our front carbon is going to look like this, just as we have it in the model. Okay. And then we've got our circle, and our back carbon is like that. And then if you look on the sides, we have hydrogens. So hydrogen, 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 hydrogen. You can put those in. And then what do we have on the top and the bottom? What's on the top? What's on the bottom and front and the top and back? Those are carbons. So we have to express that. We're not just going to put a C there. Those are CH3 groups. So just to compare to the previous structure we drew, that's going to be 1, 2, 3, 4. So carbon 1 is the one down in front, and carbon 2 is the front of the Newman projection. Carbon 3 is just behind it, and then carbon 4 is coming up the back. All right. So what happens here, and we're not going to get too far into this, but what happens here is now there's not just a staggered and one staggered and one eclipsed conformation. There's actually different ones, because you can have this staggered one where the two CH3s are completely opposite each other, but there's another staggered conformation like this where they're kind of next to each other. Now notice it's still staggered, but they're next to each other. And there's going to be a little difference in stability there. In these structures, the more you can keep the bigger groups away from each other, the more stable the structure is. So one of the reasons that we always draw this type of a conformation, as opposed to this one, is because there's actually an energy difference there. If you imagine these as big spheres of electrons as they are, these are going to start getting in each other's way. Whereas here they're nicely out of each other's way. And that type of interaction, part of it is just the fact that electrons repel each other, but actually most of it is orbital repulsion. Do you remember quantum numbers from Gen Chem? Is that a fun part? Do you block it out? What's the rule? What's the rule about quantum numbers? It was called the Pauli exclusion principle. Anybody remember that one? What did that say? But yeah, the result of it is that you can only have 2 electrons in each orbital of Y. What is it about the quantum numbers that forces you to only have 2 electrons in each orbital? Nothing? Too long ago? What? Yeah, yep. So why do you have to have those? So what happens if you put a third one in? It would have to have the same quantum number. So the rule actually says no 2 electrons can have all 4 of the same quantum number. So you have to have electrons with different quantum numbers, and that's what's happening here. That if you get these things too close, you now have electrons with essentially the same quantum numbers trying to occupy the same space, which is not allowed, and so it repels each other and becomes more unstable. So when we draw these structures, we're usually dealing with the lowest energy or the most stable conformations. But in some structures, as we'll see, we'll have to actually go into higher conformations to see that. All right. Feel okay about that? So you can practice drawing those a little bit in the homework. Seem like maybe not. But we're gonna continue thinking about this, but with even larger structures now. We're gonna look at, for our last 15 minutes, we're not gonna get too far into it, but we'll get started. We're gonna look at cyclohexane. So if you've got enough pieces, or if you need to combine a couple of groups, everybody make a model of cyclohexane. And for this one, if you're mixing and matching the sticks, you get cyclobutane.
I know.
Yeah, it's good. If you're mixing and matching the sticks, try to put all the same size stick around the cyclohexane, if you can. And then you can use different size or colors for the hydrogens. But it'll just work better if you have, I know not all of the kits have enough, but if you can get the same size piece all the way around the cycle, that's ideal. Run out of sticks here. Yeah, so I'd say like, okay, here's the structure, draw the Newman projection looking at this particular bond. Or the other way, I give you Newman projection and say draw this out on the structure. How are these cyclohexanes looking? Agreed? Okay, good. So as you're putting these together, what you might notice is that the structure is not actually planar. It's not all in the same plane. If you try to force it to be totally flat, you'll actually feel the strain on the bonds. And that's because geometrically, a flat hexagon has angles of 120 degrees. But again, we know that our sp3 tetrahedral carbons should have an angle of about 110. So if you're trying to force it into a perfectly flat conformation, there's going to be some strain there. And so in the real structure, we don't have a flat conformation. We have something like this, where that zigzag pattern continues all the way around the ring. Now, to get it in exactly the right conformation, there should be 3 bonds that are pointing straight down, and 3 that are pointing straight up, like perfectly straight, like you could set it on there if they were all the same length. And then the ones around the side are kind of going, alternating up and down at angles. Something like that. And then you should see a nice zigzag up, down, all the way around the ring. Okay, so now we're going to draw. So when we're doing what we call conformational analysis, where we're looking at the different types of conformations of the ring, it's actually important that we draw this properly. So we can't just sort of give it a rough approximation. We really need to make sure we've got all the angles right, so we can really see what this thing is supposed to look like. So there's a couple ways we can do that. One is to use Newman projections. So if you imagine looking down, like straight down two of the sides, you see nice staggered Newman projections on those sides, right? Everybody see those? So we could draw that. That one's not quite. Side up like this. All right, we're not going to mess with the Newman projection thing because that's not in the book. The book has a nice way of describing how to draw this, and one thing that I would recommend that you do, especially if you have a you can find pictures of this stuff online or just make a copy. So this is on page 77. They talk about how to draw these things. And one of the helpful things that you can do starting is to just trace it, because it is kind of a weird shape and it can be hard to get those angles just right. So I'm going to actually do that now just to show you how that works. So here's the conformations from the book. Let me, oh, that's weird, okay. These are often called chair conformations because they kind of look like a sideways, like a recliner with the feet or something. I don't know where that word comes from, but they are called chair conformations. And the way that you're going to draw them, everybody has their own method of what they like, which way they like to do it. As long as you get something that looks like that, you're good, or similar to that. What the book suggests is that you trace the two, or you draw the two parallel lines in the middle first. Because all of these chair conformations are constructed from sets of parallel lines. So you've got two parallel lines in the middle, and then you've got two parallel lines on the sides, on the left and right side, and then two parallel lines, and then the other two should also be parallel. And it's important when you're drawing these to actually have parallel lines, because that's going to influence how we draw the rest of it. So once you've kind of traced or drawn something that approximately looks like that, take your cyclohexane model and rotate it so that you're looking at it in such a way that you can see what you just drew in your model. So we're kind of looking at a sort of a top view just slightly above the cyclohexane. So we're not straight on, we're kind of like slightly above, tilted a little bit. Play with your model until you can see that in it, and then draw it on your own paper, or draw it first and then play with the model until you can see that. And you should see those three sets of parallel lines in your model, just like you do on the paper. This is really weird when you first learn it. It was one of the hardest things that I ever had to deal with when I was first learning organic chemistry. It took me forever to be able to see this and draw it. Take out the models, look at animations online. There's some like things you can manipulate with your mouse if you don't have models at home. But it is a kind of a physical three-dimensional thing. It can be hard to do without really looking at it. So then going from left to right is actually a conformational change. We call it a chair flip, but it really is something that is happening in these molecules. They can flip from one conformation to the other via bond rotation. And the way that works is if we take our first conformation over here like this left corner, like this, you can see it. This left corner is going to flip down, and then the right corner flips up, we have the other one. And if you grasp your model from the two corners, you should be able to kind of flip it back and forth like that. And notice that in each case, you have 3 bonds pointing straight up and 3 pointing straight down. And then you flip it, and you once again have 3 straight up and 3 straight down, but they're a different 3. So you can flip that back and forth. All right, so since we're getting low on time anyway, the next step is to draw in all the substituents, all the little bonds at the correct angles. We're not going to get to that today. We'll work on that on Wednesday. But for the last couple minutes, play with your model, flip it back and forth. Try to draw that shape a few times if you can, just like over and over again, just to get used to it. One of those two shapes or both of them. Eventually, you want to be able to draw both of these with the lines on there. The book also talks about this. And this is something that really just takes practice. So whether you understand it or not, it's still going to require just sitting down and drawing it a bunch of times to get it looking good. So we'll work on this more on Wednesday. Please take your models apart and put them back in the kit. Flip them back and forth a few times and try to draw those shapes. I should also tell you, if you don't like this particular technique, the other way that this is often done, or the other way that people like to do this, is to start from one corner and make the angle like that, and then draw the 2 parallel lines, and then the other side. So either way you do it, try to keep those things parallel, and it just takes practice. Yes, you see how you have these 2 up, like they're kind of pointing up? One should be down and one up. So it's like that. So you have 3 of these pointing down, 3 of these pointing up, and that's the shape. Then the other one, flip it and flip it. So you can go. These aren't great for that, but so there's the other side. What? They can, but that's a higher energy confirmation because that's more like eclipsed because those 2 things are getting close to each other. So usually the more stable confirmation is going to have one up and one down. No? You don't like this one?
No.
Okay.
I don't see it.
Okay. Do you have your model still?
No.
That's part. Okay. We'll work on it more on Wednesday.
If I pinch it, it's here.
Yes.
Is that okay?
That is fine. As long as you still have the parallel lines.
Okay.
On Wednesday, when we have a little bit more time, we'll work more on like what good ones look like, what not so good ones look like, and how you can tell if you're drawing it right or not. Yes.
Do you always have to like if you're doing it in production, you always have to list where you're looking at?
No, not necessarily.
Like how would you know that exactly? Okay. I mean I know
Because it's more dark, right? Yeah.
Okay.
So it's just, once you know how to interpret the Newman projection, which you do now, then yeah, you can draw any molecule from it and you just count the carbons or.
Because wouldn't that look different if you were looking at it? Like it's 3-1.
So the Newman projection is different depending on what you're looking at, but the structure is still the same structure.
So you don't have to like where people
Right, it should be clear the structure is drawn.
you just count the
Tomorrow I have class until 1:45, but then I'm meeting with a professor. Because I'm doing this like it's called a it's not really I just like I'm gonna present something. So we're gonna decide which paper I want to present. how long it'll take?
Thank you. Have a good day.
Okay.
Thanks.
I
Have a
mean,
good day. See you Wednesday.
it doesn't matter. Like, I can stay or like I can go home and come back. I literally live like 9 minutes here, so.
Look at this. Here, let me show you.
Okay. Yeah. Unless you like want to go alone, and that's really fine. Okay.
Yeah, so there's a couple different choices.